Hello! So on May 12th, just a few days before I'm making this video, the EHT team released the first image of Sagittarius A star, the black hole at the center of our galaxy. Long before the photo, however, there were other indications that a black hole exists at the center of our galaxy. So I'm going to dedicate this video to some of the hints that led us to taking a picture of Sagittarius A star in the first place. Because without first suspecting the existence of Sagittarius A star, no one would have aspired to get visual evidence of the black hole.
I feel like an astronaut in what you know about rolling down in the deep.
The first real detection of Sagittarius A star was in 1974 when astronomers identified a radio source coming from the Sagittarius constellation. At the time, they didn't know it was a black hole. 8 years later, the radio source was given the name Sagittarius A star because of the constellation it came from. The asterisk was a common notation for atoms that are in a high energy state, and thus the asterisk became an analogy comparing the radio source to high energy state atoms. Still, it took several more decades before compelling evidence convinced astronomers Sagittarius A star is indeed a black hole. In 2008, the Galactic Center group at UCLA calculated the mass of the radio source at the center of our galaxy by observing the orbits of stars around Sagittarius A star. By observing the orbits, the group was able to determine that the object at the galactic center had a mass of roughly 4 million solar masses. That work was so massively important that it earned both Andrea Ghez and Reinhard Genzel the 2020 Nobel Prize in Physics. Because the diameter was already known, determining the mass of Sagittarius A star constrained what its density could be. Its mass was much larger than previously expected, which meant that only a black hole could have a density as large as what was indicated by Sagittarius A star. But how can you measure mass simply by observing an orbit? Well, Kepler's third law relates the semi-major axis of an orbit to the period and mass. So we can use Kepler's third law for one of the stars orbiting Sagittarius A star to measure the mass of the black hole. For extremely massive objects, like a supermassive black hole, we can say that the mass of the star orbiting it is negligible, so the only mass we really care about is the mass of Sagittarius A star. Now, to apply Kepler's third law, we also need to know the period and semi-major axis of the orbit. Here we have an image generated by the UCLA Galactic Center group via the Keck Observatory. Somewhat ironically, the star here is the indication of Sagittarius A star, which is the only thing in this image that is not an actual star. All the little circles surrounding Sagittarius A star are representative of stars orbiting the black hole, and the star here represents the black hole itself. Let's take a look at S037. It's important to note that this image is a 2D projection of a 3D event. That means that while Sagittarius A star may lie at the focal point of the orbital plane of each of these stars, we see the orbits at an angle, and thus Sagittarius A star will not necessarily appear like it's at the focus from our perspective. For example, S037 appears to have a roughly circular orbit. For a circular orbit, the focus should be at the center of the orbit. However, Sagittarius A star appears a bit off-center in this 2D projection. We can conclude from this observation that S037's orbit is not precisely a circle. Nonetheless, we can still get a reasonable approximation for the semi-major axis from this projection. We can use the plate scale given at the bottom of this image to measure the distance from the bottom end of the orbit to Sagittarius A star in this projection. Why are we using the long end for the measurement? Because with the axis tilted, the longest part of the orbit is the best estimate for the semi-major axis. Okay, so if we measure this length, we get about 0.15 arcseconds. This is an angular size, which we want to convert into an actual distance. To do so, we can use the small angular approximation, which states that the tangent of an extremely small angle is roughly equal to the angle itself. So our angle, 0.15 arcseconds, equals the semi-major axis over the distance to Sagittarius A star, which is 8 kiloparsecs. There are 206,265 arcseconds in a radian, so we can convert our angle into radians by dividing by 206,265. The semi-major axis then becomes 5.82 by 10 to the negative third parsecs. We can convert parsecs to AU for more convenient units later on. The period is easy to measure. In 2002, S037 was at the upward end of its orbit in this image. By 2011, it was nearly at the other end of its orbit, so it took 9 years for S037 to complete half an orbit, which means it has a period of 18 years. Now we can calculate the mass of Sagittarius A star. An easy way to do this is to set up a proportion. If we set everything relative to Earth's orbit, we can use convenient units. Reorganizing our equation to solve for mass, we get that the mass of Sagittarius A star is about 4 million solar masses. Of course, as soon as the photo of Sagittarius A star was released, the astronomy community circulated the internet with memes, many of which related the portrait of Sagittarius A star to an everyday object, like a bagel or a fidget spinner. The image may appear blurry, but that only showcases what an incredible feat it was to take a picture of a black hole that is 8 kiloparsecs away from us. By the way, 8 kiloparsecs is equivalent to over 25,000 light years. That means the photo we see of Sagittarius A star is really a picture of the supermassive black hole from 25,000 years ago. That's around the time of the last ice age. It's had quite a few birthdays since then. Well, anyways, that's about all for today, so thanks for watching, and as always, ponder, wonder, and go right in the stars.
In slow motion, yeah, I feel like an astronaut in the ocean.